Alright, in this video we're going to talk about Unit 4 Objective 2, and that is concavity. So in the last video we talked about monotonicity, so increasing and decreasing. Another feature of graphs that we want to look at is concavity. So concavity tells us how a function opens. So it's either going to open up or it's going to open down. It's going to be concave up or concave down. So concave up is going to look like that or like that. Or you could put it together and it looks like a parabola with a positive leading coefficient. But each of these pieces individually are concave up pieces. So this piece is concave up, this piece is concave up. Concave down is basically going to have the two pieces that are going to combine to give you a parabola with a negative leading coefficient. So this is concave down, concave down. Some people like to think about concave up as something that could hold water, and concave down as something that would lose water. So if you put water in here, it can stay. If you put water in here, it's just going to fall out the bottom. So you can think of concave up and down that way. Our AP justification. So once again, AP is going to ask us to justify that something is concave up or down. So find the intervals on which something's concave up and justify your reasoning. So our justification for concave up, we're going to say that f prime of x is increasing. F prime of x is increasing tells us that we are concave up. Concave down, you could probably guess, f prime of x is decreasing. So let's think about that for a second and kind of look at those pictures that we just drew and see if that's going to make sense. So f prime is the derivative, so we can think of this as our function. The derivative is going to tell us the slope. So the slope is increasing, and that looks weird because it looks like we have a negative slope. So negative we usually don't think is increasing, but if we think about what we are talking about, the value of the slope, the value of the first derivative is increasing. So over here, I have something like a slope of negative 4. As we get farther and farther to the right, I get less and less negative. So this is like negative 4, this could be negative 1, then we get 0. So my numbers are getting bigger, right? They're getting less negative. Negative 4, negative 1, right? Negative 1's bigger, the number's increasing, 0, then 1, then 4. So all the way through here, my slope is getting bigger. So my f prime, my derivative, is increasing. Likewise for concave down. If we look over here, I have a slope of like 4, slope of 1, slope of 0, slope of negative 1, slope of negative 4. As we draw the graph, my slope or my derivative is getting smaller, so it's decreasing. So our AP justifications, the thing that we need to put into our brains, is that f is concave up if f prime is increasing. F is concave down if f prime is decreasing. Now there's another way that we can look at this. The way that we're going to find these things is different than how we're going to justify. We're going to justify using f prime is increasing and f prime is decreasing, but the way we're going to think about it's a little bit different. So if you remember, we needed to recall that the words increasing and decreasing meant something to us. They told us to look for something. So increasing and decreasing, they tell us to look at the derivative of a function. So when we saw a second ago that f prime is increasing, we want to look at the increasing part of f prime. So increasing means look at the derivative. If f prime is increasing, we need to look at the derivative of f prime, which means we're looking at f double prime for concavity. So when we're going to find concavity, we're going to look at the second derivative, but we're going to use the first derivative to justify. So a function is going to be concave up if the second derivative is positive. Concave down if the second derivative is negative. So we're looking at the second derivative, but we're going to justify using the first derivative. So we have a special name for the point where the function changes from concave up to concave down. So if we look at a graph that looks something like this first part of the graph is concave down, right? So this whole first part is concave down. That's a part of a parabola that has a negative leading coefficient. But then it turns into concave up, right? It's a part of a function or a part of a parabola that has a positive leading coefficient. So the red part's concave down, the black part's concave up. So there's some point right there where we're going to switch from concave down to concave up, and it gets a special name. We're going to call that a point of inflection. So we change concavity at points of inflection. So let's look at an example, and then we'll call it quits on this video. So find the interval or intervals on which f of x equals e to the negative x squared is concave up or down. So concavity, justify it with the first derivative, but we're going to find them with our second derivative. So to find a second derivative, we need to find a first derivative. So our rule for e is u prime e to the u, and in this case u is negative x squared, so u prime is negative 2x. So we're looking at negative 2x e to the negative x squared. That's our first derivative. We need to find when our first derivative is increasing, when our first derivative is decreasing, so we need to look at the derivative of the first derivative, which is our second derivative. We now have product rule, right? So we have a 2x and an e to the negative x squared, so two different functions, each of them have an x. So the derivative of the first part is going to be negative 2 e to the negative x squared. And then plus the second part, so plus, keep the first one the same, so we'll say negative 2x. The derivative of e to the negative x squared we already found was this thing here, so we know it's going to be negative 2x e to the negative x squared power. So we can simplify this a little bit. So negative 2e to the negative x squared. Negative 2x and negative 2x is going to be a positive 4x squared e to the negative x squared. We can factor because we need to find increasing and decreasing for the first derivative. We need to find when the second derivative is positive and negative. And just like our number line from before when we were trying to find increasing and decreasing, so the first derivative positive and negative, if we're trying to find the second derivative positive or negative, we're going to need a number line. And we're going to need to find when we change from positive to negative. So really we need to find when this thing is equal to 0, just like before when we needed to find when our first derivative was 0 to find increasing and decreasing. So I'm just going to rewrite this since we have the 4x squared here. So to solve that, when that's equal to 0, we can factor out an e to the negative x squared. And we're left with 4x squared minus 2. This piece here is never going to be 0. E, a positive number raised to a power, I don't care what the power is, never going to be 0. It's also never going to be negative. Right? This is always a positive number. It might be really, really small, but it's never going to get to 0, and it's never going to be negative. So when we're trying to solve this, really we need to look at just this piece, and we know that this is going to happen. This is going to equal 0 when x equals, so add 2, divide by 4 is 1/2, take a square root, plus or minus square root of 1/2. So now we just make our number line. We have a negative square root of 1/2 here, a square root of 1/2 here. We're going to want to label our number line. So we're trying to find concavity. So we want to put this into our second derivative. Now we know, because we solved this, that our second derivative is 0 at those 2 points. So now we just got to take numbers, plug them in, and see what happens. So taking something less than the square root of 1/2, let's just say negative 1. Take negative 1, plug it in. Remember, this first piece, the e to the negative x squared, is always positive. So we don't even have to worry about this. It's all going to depend on this piece here. So negative 1 squared, 1, times 4, 4, minus 2, 2, positive numbers. So I know I'm always going to be concave up from negative infinity all the way over to negative square root of 1/2. Between square root of 1/2, or negative square root of 1/2 and square root of 1/2 is, well, let's take 0. That's going to be the easiest number. So 0 squared is 0 times 4 is 0 minus negative 2, or sorry, minus negative 2. Minus 2 is negative 2. There we go. Negative numbers in here. So we know we're concave down from negative square root of 1/2 to square root of 1/2. Take a number bigger than 1/2. Let's take 1. Plug it in. We're going to get positive numbers. So we know our second derivative is positive, then 0, then negative, then 0, then positive. So concave up on the intervals negative infinity to negative square root of 1/2 and square root of 1/2 to infinity. We're going to say concave down from negative square root of 1/2 to 1/2. If we had to justify, we would say we're concave up on these intervals because f prime is increasing. If we had to justify this, we would say concave down because f prime is decreasing. If the problem asks for points of inflection, we can say that those happen at x equals negative square root of 1/2 and square root of 1/2. And if we had to justify that, we can just say that f prime changes from increasing to decreasing and decreasing to increasing at those points. So that'll do it for this video. We'll see you in the next one.